Okay, so I'm pleased to talk to you today about the Gossamer Condor and Gossamer Albatross human-powered airplanes. Uh, this talk describes the development of two human-powered airplanes that were very successful, and they involved original thinking and depended very little on prior human-powered airplane designs or conventional airplanes. And so this talk just sort of shows the history, and my hope is that it provides a kind of foundation for current efforts, especially in universities. This talk is truncated from a prior talk which included two solar-powered airplanes. This chart shows the timeline of these airplanes: the Gossamer Condor, the first Gossamer Albatross, a second backup Albatross, the Gossamer Penguin, which was originally a smaller version of the Albatross that might fly across the channel if it turns out to be too windy for the Albatross, and then the Solar Challenger, which was a manned high altitude, long distance solar powered airplane. And you see that all of this action happened in about 5 years. The multiple lines indicate iterations of the design or stages of the design, and the triangles indicate periods of operation. So it's a little sketchy. The Gossamer Condor, as an introduction, was purely human powered. It won the Kramer Prize, a 50,000 pound, which used to be a lot of money, prize for a figure-8 flight around two pylons half a mile apart. So the total flight was at least a mile and more like 1.2 miles. The span of this airplane is 96 feet, which is maybe 29 meters. And the weight of the airplane, the empty airplane weighed about 75 pounds and the pilot weighed 135 pounds. And I will let you guys do your, well, what is that? That's maybe 97 kilos or something. And it flew on about 300 watts and operated in 1976 and 1977. The Albatross was also human powered, and it won a second Kramer Prize for crossing the English Channel, 100,000 pounds this time, although it wasn't worth twice as much because of variations in currency. And this flight was 22 miles upwind, which is important. It had a slightly shorter span, slightly more weight, but the same pilot who hadn't gained any weight, and flew on only about 225 watts. And this happened in 1978 and 79. And then there was a second Albatross that was completed and used for research by NASA in the period 1980, 1981. The equation for airplane power is basically drag times speed divided by prop efficiency. And if you do an equation, an approximate equation for that, you get this flute music in the first line there. But if you simplify this, what you see is that power is proportional to the weight of the airplane to the 3/2 power divided by the wingspan and the prop efficiency. So what you're striving for, what is crucial in human powered airplanes, is very or extreme lightweight. Also, a very large span, which of course is in conflict with weight, and high prop efficiency, which is achieved with a very precisely made rigid propeller, which of course is in conflict with weight. And then other ways to get low power would be to provide a wing with a very high lift coefficient, which requires a precise and possibly heavy wing. You can also get laminar flow, which also requires a precise wing, which is heavy. And you may be able to get a very high Oswald efficiency factor pertaining to induced drag. And that may be achieved by a proper lift distribution or by operation and ground effect. And that's an area that hasn't been explored very much in human-powered airplanes. Now, getting into the background of the people involved in this effort, Paul McCready, Dr. Paul McCready, was an engineer. He's passed away now some time ago. He had a lot of experience with models as a kid, and Brian Allen started training for his flight at an early age, as you see in the lower right corner. Also, Paul McCready had experience building in the lower right corner ultra lightweight rubber powered models. This model you see here has a span of maybe, I don't know, 50, 60 centimeters, and it weighs a gram. And that includes the motor. And notice it has a thin single surface wing and tail skins and a huge propeller. The color in that wing skin is there because of interference patterns with light in the same way that an oil film generates color. Paul McCready was a two-time national championship in the United States in soaring and one-time world champion. And he said that he was not a great pilot, but what he had done was figured out the underlying math and figured out how to fly at optimum speed to go cross country. And he invented the McCready speed ring, which is still used electronically today. Also, at the time of the Gossamer Condor, and just before that, Paul McCready was a hang glider, as were his kids, and he was familiar with the wire-braced cruciform structure of the hang glider. So these are all important components of the background of this airplane, or these airplanes. And Brian Allen was a skillful hang gliding pilot. He was also into bike riding and bike racing, and did study biology in the university. Notice that he's quite slender, even though he's about 6 feet tall. He only weighs 135 pounds, which is roughly 61 kilos. The early Gossamer Condor is very similar to that single surface rubber powered model I just described. This airplane has wire bracing, a huge propeller, and a single surface wing with quite a bit of camber. And this airplane flew successfully, but not very far. And it had tremendous sensitivity to turbulence, even small turbulence, because it would separate the wing either on the upper surface or on the lower surface. And here you see Paul McCready sort of helping the pilot along at a almost walking pace. This airplane was incredibly slow and very lightweight, and also notice that it's very crude and simple, which made it easy to modify and easy to repair. The Gossamer Condor was flown, the first flights were out in the desert where the weather is less stable and more subject to wind. The project moved to the south end of the San Joaquin Valley at Shafter, California. And that valley is it's surrounded by huge mountains and tends to be still or even stagnant, and often smells like pesticide from all the farming that's going on there. The Condor there in Shafter had many successful flights, and the airplane was evolved in an iterative way via crash and rebuild. If a component, and many of the crashes were the result of a component failure. If the component broke, it was strengthened, and if it didn't break, it was lightened. And so that evolution yielded a very light but successfully strong airplane. An advantage of this kind of low altitude, slow airplane is that you can crash without killing anybody or even seriously injuring people. So it was good in that way. the primary structure was aluminum tubing. Most of it was 2 inches in diameter. That's about 50 millimeters. And it was chem milled, that is to say, acid dipped to reduce its wall thickness down to about 0.015 inches, which is a third of a millimeter. So very thin. And these walls were subject to buckling and crippling, and they were reinforced with discs of rigid, low density foam to keep them from crippling. The wing was covered with mylar, which is a polyester, that's a DuPont product, a polyester film used then for magnetic recording tape. Some of you might remember that. And the upper surface where the forces were higher was 1/1000th of an inch thick. So that is 1/40th of a millimeter. And the lower surfaces that were less, had less pressure differential on them were half that thick. There was a lot of tape used in this airplane to connect the mylar primarily, but then also other components. And the leading edge was wrapped for aerodynamic precision with single-sided corrugated cardboard. So the paper side was on the outside and the corrugations were on the inside, and that enabled it to bend around the very few ribs that were positioned. And here you see Brian Allen in the airplane. He's recumbent, and I'll talk about the controls in just a little bit. Now, here is a 3-view or general arrangement drawing of the Gossamer Condor in its final form. And just to show this a little bit, what you see is a very small spar that's supported by many flying wires in a cruciform shape. There's vertical, lateral, and longitudinal struts, basically, and all of these are wire braced to each other to make it rigid in all axes. The trailing edge of the wing was just a very thin wire, about 0.5 millimeter in diameter. And it was tensioned by tensioning the mylar film, which is heat shrunk with a heat gun. So this whole thing was in balance. You could change the wing sweep by changing the length of those forward wires you see in plan view, which would tighten the trailing edge wires, and you'd end up re-shrinking the wing. So it was tunable after the fact. Now this shows, so after the Gossamer Condor won the Kramer Prize in 1977, if I'm not mistaken, the Royal Aeronautics Society and Kramer figured they would fix our wagon by setting a Kramer Prize for crossing the English Channel, which of course is much, much, much more difficult. However, I'm not sure they understood that a modest refinement of the airplane could drop the power level down enough that you could fly long enough to get across the English Channel. So this airplane is basically a refinement of the Gossamer Condor with a considerably less wetted surface, a more precise airfoil that worked at a higher lift coefficient, and other refinements. In particular, the propeller in the end was much better, and that's important. So you could, if I go back and forth, you can see how similar they are, but also how much more like a sailplane the Gossamer Albatross is, and how in general, since then, the evolution of human-powered airplanes has been back towards sailplane configurations, except executed in extremely light materials that allow them to be both clean and light. So here's the early Albatross at Shafter, sort of at this stage, it was a test airplane. It had no joints to transport the airplane, except the wing came off the fuselage, and it had the Gossamer Condor style wooden propeller. And once again, you can run to keep up with it, but it was a bit faster, so you had to run a bit harder. And here Parker McCready is flying. And again, this is at Shafter, and again, it was mostly a group of volunteers helping to build and fly this airplane. And so there was sort of a crew of volunteers that made for nice time. We'd fly in the morning until it got a little too thermally, and then go off in the afternoon to find some recreation, like in the local river. So at some point we moved to a Navy amphibian hangar at the port of Los Angeles, adjacent to the water, with the intention of flying over the water. There was enough space in the vicinity to test fly over land, and in the end, we never did fly over water until we launched to fly across the channel. And here you see the Albatross with the multi-piece wing now, and the fuselage standing on the far right. The tape layout lines were used for constructing things. So here is the takeoff location on the Warren. It's a big concrete pad protecting a small shed. Well, it's not that small, which is pointed out by the arrows. And this was a typical day in England. I mean, we, as Californians, we had no understanding of how wintry or strong the weather in England was. So we waited a long time for an appropriate day. Now switching a little bit, want to show the Albatross controls and instruments. The upper left picture is the canard tilt and canard pitch controls. Once again, this by rotating this handle, you could directly pitch the canard, and by rotating it, in roll, it would roll the canard. And then in the upper middle picture, there is a handle, a tape wrapped handle with a spool on it, and that had the flying lines for the wing to do the wing twist. And I believe this had a trigger to lock it in position so you could turn it and then pin it. On the lower left is an airspeed indicator and an altimeter. The altimeter was an acoustic altimeter taken from a Polaroid SX70 camera. And the battery for this system failed at about 2 hours, which was the anticipated flight duration. So the last 49 minutes of the flight were done without feedback in terms of airspeed or altitude. And the early developmental controls were on the right. What you can see from these pictures was that this airplane was intended to win a prize. It was not intended to win a prize for flying across the English Channel. It was not intended to win a prize for beautiful construction. So in contrast with Mark Drella's later airplanes, which were built on a time and materials basis, those airplanes were immaculate and exquisitely constructed. The Albatross, by comparison, was slapped together. Nonetheless, the important stuff was well attached. So now, finally, the adventure. We're on the concrete apron of the Warren, and we laid out it. The concrete surface was very rough, and we laid out masonite. And this was the first time we'd ever taken off of masonite and discovered that the landing gear wasn't perfectly aligned, and we went right off the side because it turned into the largest hole in the concrete, broke the nose gear, but we're able to repair that. And the second takeoff was the charm. And so now you're looking back from the boat towards the cliffs. This is sort of the white cliffs of Dover. as the airplane takes off. And I was in the center boat that trailed behind the airplane, and my job was to rescue the pilot if he went in the water. I had lifeguard training and was a decent swimmer. So that was my job. And of course, I was paying attention. And I was also the biggest fan of Brian succeeding after Brian, I think. So here we are heading out. And this was a very surreal moment to see this thing float out across the water with press boats and the lead boat out in front. And then we had 3 or 4 Zodiacs to rescue him and to guide him and to, in the end, fend off the press boats who always wanted to get too close. But then the wind starts to pick up. And you know, sailors can tell from this texture that there's some wind here. And of course, it's a headwind. And the decision was made to give up because the turbulence from this wind and the headwind was increasing the power level needed. So Brian pulled up. There was a little tiny hook by the nose gear, and Bill Watson in the orange suit had a fishing line with a kind of loop on it that was supposed to hit that hook, and then the boat was going to race out and tow the airplane back to the base. And how that was going to work, we had no idea. We never ever towed this airplane. We never ever had been above water. But this is kind of a neat pair of photographs, because you see Brian, excuse me, you see Brian up above Bill Watson trying to snag him. And in the front of the boat, Otis Imboden, a National Geographic photographer, is leaning back, making the picture that you see on the right. So, but in the end, when Brian went up higher, he discovered the turbulence was quite a bit less up there and concluded he could keep going. So he was actively trying to dodge Bill. So we kept going. So here's a photograph made by somebody else. This is a photograph of his photograph showing the approach. And you see that there's a big cliff in Cape Grenade, and the wind is spilling over that cliff and making a lot of turbulence. So you can see here the wing is twisted and the canard is way banked, and it's a scary moment. And here the canard's the other way, and I'm in this chase boat. I'm the only guy without a helmet because I'm ready to jump in. And then the airplane approaches the shore, and you can see the cliff. And there was a beach, which was not there 15 minutes later because of the very rapid tide changes. And he made a beautiful little landing. It got calm once he got to the beach. And in December, we went to the Royal Aeronautical Society, where we were presented with bronze medals, and Paul McCready met Prince Charles. And that was sort of the conclusion for this particular adventure, which was followed by some solar-powered airplanes. The Gossamer Penguin was turned into a preliminary solar-powered airplane, and then later a Solar Challenger, which flew at 10,000 feet and 45 knots from about 200 miles from not so far from Paris to southern England. And many other airplanes and vehicles followed that were stimulated or supported in some way by these efforts. And they're shown here. The GM Sun Racer that you see here won a solar powered race in Australia. That vehicle was heavily executed by AeroVironment, Paul McCready's company. And then there's some references here. In particular, I want to call your attention to the Gossamer Odyssey book by Morton Grosser. That is a very, very good resource and a pleasure to read. So that concludes my talk. I'd be happy to take questions. And I apologize for running so long.
No. It was very interesting. So that's why we are completely listening you. We are disturbing. So we will thank you
thank you very much for this opportunity to share. I appreciate it.
Thank you,
Okay, it
Blaine.
was a pleasure for us too.